Hello and welcome to Maths with Jacob. This lesson will focus on applying differentiation part 4. A special puzzle to warm up the brain cells is on the next slide. The answer will be given at the end. Enjoy. What is the meaning of the following? Good luck with it and see how you go. Differentiating twice. We have seen how to differentiate a function once and how this helps us with stationary points. We will now see how to differentiate a function twice and determine what information this gives us. This is also called the second derivative. So when you differentiate twice, we can refer to it as the second derivative. The symbols for differentiating twice, or for the second derivative, can be any one of the following: d squared y dx squared, or this one, the function x with 2 dashes, or the y with 2 dashes. Example, let's consider function x equals x cubed plus 4x squared plus 5x plus 7. The first derivative, when we differentiate once, gives us that. And the second derivative gives us 6x plus 8. Let's consider a point on a curve. Now, it's very important. We're talking about a particular point on a curve. If at this point we have d squared y dx squared is greater than 0, the curve is concave up. If d squared y dx squared is less than 0, the curve is concave down. If d squared y dx squared equals 0, we have a point of inflection. I'll explain what that means in a moment. First example, find the stationary points on the curve represented by function x equals x cubed minus 3x squared minus 9x. So the first derivative, function dash x, is 3x squared minus 6x minus 9. We'll continue on the next slide. Now the stationary points we saw earlier occur when function dash x equals 0. That is, when 3x squared minus 6x minus 9 equals 0, we factorise by taking the 3 out, and we further factorise to have this line here. So this expression here is equal to 0 when x equals plus 3 or when x equals negative 1. So that's where the stationary points occur, where x equals plus 3, 1, 2, 3, there, x equals 3, so there's a stationary point, and where x equals negative 1, which is here. Now, to find the nature of these stationary points, we find the second derivative. So remember, the second derivative was 6x minus 6. That's what it is. Because if the first derivative is 3x squared minus 6x, the second derivative is 6x, 2 3s are 6, 6x minus 6. So there's the second derivative. Now let's see what happens. What's the nature of the stationary point when x equals 3? So we substitute that in the second derivative and we get 12, which is greater than 0, so the curve is concave up. See that? The curve is concave up at that stationary point. Now we substitute x equals negative 1 and see what happens. See here? That's where the next stationary point is. And we get function double dashed minus 1. So when we have the second derivative, we substitute minus 1 in. We get negative 12, which is less than 0, so the curve is concave down. So there it is there. See that? The curve is concave down. So that's how the second derivative helps you. When you're looking at the stationary points, it lets you know whether the curve is concave up or concave down. Now we have more information on the next slide. A point of inflection. Now here was the original function, here is the first derivative, and here is the second derivative. We saw earlier that a point of inflection occurred when d squared y dx squared equals 0. That is, when 6x minus 6 is 0, when 6x equals 6, or when x equals 1. So the point of inflection is here, when x equals 1. Now you can see what's happening. We have the curve here which is concave down. At the point of inflection, the curve changes and it becomes concave up. And that's why that's called a point of inflection, and it's at the point x equals 1. Here's a quick quiz to help you. Please check through the video at any time. The answer to the puzzle. What is the meaning of the following? Hitting below the belt. I think you might have got that one. And here are the answers to the quick quiz, and the video is at your disposal.